Today, we're going to connect the dots between two worlds that seem miles apart. We're going from the abstract mathematical laws that put a ceiling on any kind of intelligence, all the way down to the brutal, high-stakes race to build the actual silicon that powers our AI future. We're linking the idea of AI to the engine that makes it run.
AI right now just feels magical, doesn't it? It's accelerating so fast it seems like there are no limits. But what if it's not magic? What if there's a map, a hidden set of rules that governs this whole explosion? Well, that's exactly what we're here to uncover. The fundamental physics of intelligence, from pure logic all the way down to the hardware.
You know, to really get a handle on where AI is going, you need a solid way of thinking about it. So we're going to build one, right here, by putting together two really powerful sets of ideas. Together, they explain both the limits and the engine of AI's incredible growth.
So on one side, we have the formal foundation. Think of these as the timeless mathematical laws of the universe for computing. And on the other side, we've got the practical bridge, the real-world engine of scaling that is literally shaping the chips in our data centers as we speak. Let's start with that formal foundation.
So, before we can even talk about how fast AI is moving, we have to understand the landscape it's moving through. We need to know the rules of the game, the absolute unchangeable limits of what any intelligence can ever hope to do.
The absolute outer boundary, the edge of the entire map, is something called computability. Thanks to the legendary Alan Turing and his famous halting problem, we know that some problems are just fundamentally unsolvable. No machine, I don't care how powerful it is, can ever crack them. And this isn't a technology problem we'll solve one day, it's a hard limit of logic itself. This is the edge of the universe for computation.
Now, what's super interesting is how we make progress inside that boundary. We take a hard problem, we figure it out, we mechanize it. We basically turn the solution into a new tool, which upgrades our abilities. But here's the kicker. Solving one problem doesn't mean you've won the game. It just reveals the next layer of even harder problems that you couldn't even see before. So progress is this constant cycle of climbing a hill only to get to the top and see an even bigger mountain waiting for you.
But of course, there's a catch. Just because a problem is computable doesn't mean we can solve it before the heat death of the universe. This brings us to a crucial inner boundary, feasibility. This is the line between what's theoretically possible and what's actually practical to solve in what computer scientists call polynomial time, which is just a fancy way of saying in a reasonable amount of time.
And this inner boundary, it isn't just a simple wall. We hear a lot about P versus NP, the easy problems versus the hard ones. But the reality is a lot more interesting. It's more like a structured climb, a staged descent through different levels of difficulty. It's like a ladder.
And this ladder, the polynomial hierarchy, shows that climb perfectly. At the very bottom, you've got P. These are problems we can solve directly, really fast, like sorting a list. The next rung up is NP. Now here, finding the answer is hard, but checking if an answer is right is super easy. Think of a Sudoku puzzle. Solving it might take you forever, but checking a finished one, that's a piece of cake. Each rung you climb up this ladder adds another layer of complexity. This entire ladder, this is the playground for all feasible intelligence.
Okay, so now we have our map, right? We have the absolute outer limits, and we have this inner ladder of what's feasible. This explains the structure of progress, but it doesn't explain the velocity, the absolutely insane speed we're seeing in AI today. So what's the real-world engine that's pushing us up that ladder so incredibly fast?
And this is where the theory hits the road. We're now going to connect all those abstract limits to the messy, empirical, economic reality that defines how modern AI actually gets built.
The engine is driven by a surprisingly simple but incredibly powerful idea, scaling laws. Now, this formula might look a little intimidating, but the concept is dead simple. A model's performance, which we measure by its loss, basically how many mistakes it makes, gets predictably better the more compute power you throw at it. Loss goes down as compute goes up. It's this predictable return on investment that explains why companies are pouring billions and billions of dollars into training these huge models.
But, and this is a huge but, there is a catch baked right into that formula: diminishing returns. Every new leap in performance requires a massively bigger jump in compute than the last one. The cost of making progress starts to skyrocket, and this creates this immense, relentless pressure to get more and more efficient.
So how on earth does progress keep going? Through compounding efficiency. It's this constant, three-front war to innovate across the entire stack. You need more efficient chips, sure, but you also need smarter algorithms, and you need better system software to tie it all together. All of this work is about one thing: making each bit of computation do more work. It's how we keep climbing that scaling curve without going completely broke.
And that relentless pressure for more and more efficiency has a direct physical consequence. It fundamentally changes the chips we design. It kicks off an incredible architectural race to build the best possible hardware for AI.
Now, to understand this race, you need to get one key concept: the value scalable fraction, which we'll just call S. This is a modern twist on an old computer science idea. It's not just about what part of a task you can make faster. No, it's about the part where adding more compute genuinely creates more value, like a better translation, a more creative image, or a more accurate prediction. And for modern AI, this S value is huge, and it's only getting bigger.
And that brings us to this critical formula. I know, more math, but hang with me, because this little equation governs the entire hardware race. S is that value scalable part we just talked about. As S gets closer and closer to 1, meaning pretty much the whole task gets better with more computes, the number on the right side of that equation gets astronomically huge. That number is the bar that a specialized custom chip has to clear. It means a special chip needs a massive efficiency advantage just to be worth its own inflexibility. If it can't clear that bar, you're actually better off just using a more general flexible chip.
You can picture it like this race. The flexible, programmable GPU, that's one car. A custom-built, specialized piece of hardware is the other. As our AI tasks get better and that S value grows, that red line, the collapse threshold, it just keeps rising higher and higher. If the specialized chip's advantage drops below that line, it's left in the dust. The winning strategy then becomes putting all your money and effort into the flexible hardware.
The real-world consequences here are just profound. This whole dynamic explains exactly why we see GPUs becoming more programmable, not less. They have to keep adapting to chase this moving target of value. The entire industry is being forced to shift towards flexibility. Now, specialized chips aren't dead, not by a long shot, but they face this brutal, ever-rising bar to justify their own existence.
So we've journeyed from the most abstract logic all the way down to the most concrete silicon. Now let's put it all together and see the complete, unified picture of how AI progresses.
And here it is, the whole arc. It all starts with those absolute formal limits. Inside those limits, we find the ladder of feasibility. Powering our climb up that ladder is the relentless scaling engine. And the physical, real-world result of that engine's pressure is the architectural race, which is constantly reshaping our hardware to favor flexibility. You see? It's a complete feedback loop from pure logic to physical hardware and all the way back again.
So it turns out progress in AI isn't magic after all. It follows a map. It's a structured process with formal boundaries, real-world engines, and physical consequences. We understand the rules of the game now. So the question is no longer if we can climb higher, but where we, as the architects of this technology, choose to point it next.